So within our fifth lecture on the equilibrium constant, we had introduced once more formally the notation for reactions in terms of stoichiometrical factors and components A and B and C, etc. for reactants, and X and Y products. Right? So here we just specify two to exemplify things. Should be straightforward to generalize this to any number of components. We had then discussed our progress variable psi and used it to define the differential coefficient in our total differential for the free energy, right? So in particular, you see down here our dg, given that there's no work and things are isothermal, the only thing that can happen under those conditions is chemistry. Right? And so that's why we need psi. And this derivative of G with respect to psi is something we call the change in Gibbs free energy per mole, this delta Rg. Okay. So strictly speaking, this psi is just for an infinitesimal small change or advance in the reaction, but we want to discuss the equilibrium situation. So this is where this is relevant. So in particular, it connects really, as you can see here, directly product with reactants. Okay. So the actual path of how your reactant to the product is going, right, which is something I believe my postdoc told you about in the last lecture on Tuesday, right? This was a way to find the transition state geometries. All of that is irrelevant for us. The only thing that matters is the difference between the reactants and the products. So this is what determines your equilibrium constant, right? In order to determine also the reaction transition state, the barrier, which allows individual species to go from reactant to products, right? This is a whole different set of problems, right? This is what you would study in kinetics, right? As these barriers impact the time it takes for your reactants to transform into products. However, in the equilibrium thermodynamics, we don't care about time, and we consider everything to be in equilibrium. And so you have a ratio between reactants and products concentrations, which is independent of time and which is solely determined by the difference in free energy between reactants and products. And this difference is what you see here in this bracket, right? So we had identified this as the weighted sum over stoichiometrical factors of reactants and the difference to the weighted sum of geometrical factors of products, and they are weighted by their chemical potential, which is the chemical driving force. So this picture, I hope, is if it hasn't yet been already in your mind, I hope it's now deeply ingrained, because this is really what rules, predominantly rules all chemistry. If the barriers are not too high, this is what totally governs what you would see. We had then continued to express our delta G via this expression for our chemical potential, which we had obtained previously. and we had rearranged to form everything in terms of first partial pressures. And so here you have your delta Rg equals RT logarithm of ratio of pressures. And then in this equilibrium, right, your delta Rg0 is then equals this RT logarithm. And now for your partial pressures, you can simply make use of the ideal gas law. And so you replace the ratio between pressures by a ratio between concentrations. And since this happens at the same temperature, right, reactants and products are in the same, have the same temperature, that cancels as well as the R, of course. And so you're left only by the difference in concentrations. And this ratio of concentrations of reactants and products is also known as our equilibrium constant. So we had briefly discussed this for the example of the Haber-Bosch process. And this is how it's linked to the free energy. And now, today I'd like to discuss how this K is more explicitly then linked to the equilibrium constant, to the partition function Q. So this is subsection 5.3. And this in particular allows us, by merely inspecting the spectrum in coming from a Schrödinger equation, we can draw conclusions on, at least qualitative conclusions, on what the equilibrium constant should be. And if the spectrum is, of course, given quantitatively, you can also calculate it. So that's what we're going to discuss today. Are there any questions on that? Again, if you have a question, just unmute yourself, interrupt me, or raise your hand. Otherwise, I'll just keep on going. So let's now discuss this link to the partition function. So we had the Helmholtz free energy written as minus KB T logarithm Q. Okay. This was in the beginning of this chapter. And from that, we had seen that our mu is the derivative with respect to particle number. And so we had already discussed that this is minus RT dn logarithm Qn to the n, or Q to the n over factorial n, and that this is the same as minus RT logarithm Q over n. And we had also discussed that this, all of this is also equals dn of G. Okay. So this is a little recap. And again, I also mentioned that already. This first expression we call the Monsieur bridge. Which really links this crucial quantity, the partition function, explicitly to the free energy, which freely, according to Boltzmann, governs this world. So we can see that because of this mu being related as such with these thermodynamic state functions, this must also be a function of the temperature. Right? And that's something which has great implications. In particular, something we could do is we say we write our reaction-free energy for some component, right? So there's a consequence. We can write it as a reaction energy of that component at T equals 0 plus the temperature dependent contribution for the chemical potential. And this would hold for all components I. Right? So this would basically say we have the zero temperature contribution and the contribution at the higher temperature where we're actually doing our experiment. And so this is, if you look at the free energy for T equals 0, this we can also define to be delta E 0I. 1 second, please. My apologies. I had to quickly do something. So we were here at the place where we had introduced this reaction-free energy at 0 Kelvin, and this is really very much simply the energy. So the internal energy at 0 Kelvin, and in particular the difference between the reactants and the products, right? Now, if we go to the isobaric case, where we consider the Gibbs free energy, then instead of the internal energy, we are talking about the enthalpy. And so this is really corresponds to the 0 Kelvin enthalpy. Oh. Difference. Now, if you were to work in an isochoric regime, then you could or should use the internal energy U. Now, we also know that our delta RG equals the sum. No, sorry. So the delta RG the total delta Rg corresponds to the sum of the delta Rg's of each component times the stoichiometrical factor of the corresponding component, right? Which also takes care of the sign, right? If you are depleting one or if you're growing one, that is, they carry opposite sign. And accordingly, we can insert this equation above and we obtain delta I nu I delta Rgi at t equals 0 plus sum over nu I mu I. Okay. And we can then simply call this entire sum here our delta E0. Okay, so this is basically the zero energy zero Kelvin contribution to the energy difference. And yet now you have here, when we insert our expression for mu, a sum over our components mu I, and now the logarithm of I over n. I forgot the RT in front of this. Okay. And at the same time, of course, we know that all of this has to be equals RT, logarithm K. Okay, that's what we've shown last time. So we can now, because these two are equal, we can write, we can divide everything by RT, and then we have the logarithm of K being equals to minus delta E0 by RT. And sorry, the convention here is, and this whole thing is minus RT logarithm K. And so divide here by minus RT. Yeah. And then you have, and now I take the logarithm and I pull the summation inside of the logarithm. So I take my product over all the components, and each one of them has to be raised to the power of nu I. Right? Yeah. Now I have two terms. One of them is a logarithm and the other one is fraction. And if I look at this, of course, I can also express it as a logarithm. I can say this is the logarithm of e to the minus delta E0 over RT, right? And if I insert that, I can remove all the logarithms, right? So I can, let me write it like this, logarithm of e to the minus delta E0 over RT times product over Qi over n to the power of I. And this is the argument for my logarithm now, okay? And also on the left, I have the logarithm of K. So I raise everything to Euler's number as a power to Euler's number, and then I get my equilibrium constant to be e to the minus delta E0 RT times product I QIN, the new I. Now, this is written again in the generic way, namely that the stoichiometrical factors, and here take care the sign factors tells you if reactant or product. Okay. And we can make that more explicit by writing down the fraction for the two explicitly. So we take the product over all products. And we divide it by the product over all react. Yeah. And so this is a good way to think about your equilibrium constant, right? There's a prefactor in front, and this prefactor is shrinking with the exponentially fast. It shrinks with your energy difference becoming smaller, right? And so if your energy difference is 0, then your prefactor is 1, right? And you have the two partition functions only as a ratio. If you now imagine that the Schrödinger equations, the spectrum for reactants and products are the same, right? Then you have the same partition functions in the numerator as in the denominator. And then your equilibrium constant is 1 and nothing happens, right? And any distortion then drives you away from 1 to be larger or smaller, depending on what's favorable. So let's discuss a little bit more such kind of interpretations, right? Or are there any questions so far in the derivation or the steps? Are they clear? Question? How can the chemical potential drive a reaction if it has a positive contribution to G? So it's really about the difference in chemical potentials, the chemical potential on your reactant and on your product, right? So it's this balance, right? If you look at this equation from last time. Now, where is it? Consider this bracket really, right? right? It's this bracket which will determine the sign of your overall free energy change, right? And if that sign is negative, then the reaction will occur, right? You will have more reactants than products, more products than reactants, and you will hence see that the equilibrium constant must be larger one, right? And vice versa. Right? If it's positive, then your numerator will increase for the equilibrium constant. Does it make sense? Or? Okay, great. Please don't hesitate to ask, really. As I always say, right? Chances are somebody else has the same question. No? So it's always good to clarify things. Now, let's go to the interpretation of this result here. And it's fairly straightforward. So already, so your delta G, right, is minus R logarithm K is delta H minus T delta S, right? Which we know already from general for general thermodynamics for any process, right? And so what this now means is really that if we go back again to our logarithmized version and we insert it, right? So and we let's again we divide by minus 1 over RT, and then you get the logarithm K, right? So that's minus E delta E 0 over RT plus this logarithm of the products of our Q over N, right? And that's the same as delta H minus delta H over RT plus delta S over R. Okay. And so this is now very clear what these terms are referring to, right? These two guys are the enthalpic terms. Right? And these two guys are the entropic terms. Right? Now these enthalpic terms are divided by T, right? So it's enthalpic terms over T. And these entropic terms, they grow with T, right? So they are proportional to T. So this is quite clear now how this expression, this box expression we have seen before, how these two products, the exponential prefactor and the ratio, what they are standing for, right? What kind of physics they embody, right? Okay, so this is the first part of the interpretation, right? And now as a second part, we'd like to consider some cases. All right, where we will look at simple examples, right? So in particular, let's take some component in gas gas phase that transforms into another species and gas phase, right? And we want to consider this with delta E0 being close to 0, right? So negligible enthalpic contribution. Now, what could this be? Let's consider an example. So, for example, consider a molecule with a double bond. Which once has a trans and once a cis form. Okay. And to make this interesting, we decorate one of the methyl groups by another bunch of substituents. So let's say we have another set of methyl groups here and also here. Yeah. So these two species have roughly the same enthalpy, right? If you started to count the bonds in the two isomers, same number of covalent bonds, right? Same types of covalent bonds, right? Hardly any difference. So this could be our species A, species B. However, the conformational flexibility in these two species is very different, right? In the one case, if you consider the rotations around the single bonds, right, on the left-hand side, clearly there will be some steric hindrance in your rotations due to the presence of these three methyl groups here. Let me denote them even more explicitly, right? So if you consider the three hydrogens here, on the other side, then clearly there will be some blocking, right? While on the right-hand side, you can freely rotate these two groups. So what this means is the free rotation leads to much more microstates, right? And so if I look at these torsional energies, right, which are typically part of the vibrational spectrum, right? Your three internal degrees of 3n-6 internal degrees of freedom, then we would expect for E0 more or less the same energy, right? But on the left-hand side, you would expect a much coarser spectrum, while on the right-hand side, many more microstates are possible, right? Now, you also know that the probability of occupying these states decays exponentially with the energies, right, with the eigenvalues. So if I plotted my probability here, right, so hang on, let's denote this properly, right? So this would be your 0th, 1st, 2nd, 3rd, 0, 1st. Okay, it's too dense. I don't know. And so on, right? But my probability, if I plot my probability, my Boltzmann probability, right, it decays rapidly. We already discussed this, right? And the lower states are most populated. So this means then if I have few states, right, I'm just summing up these few values. If I have many states with the same probability, I'm summing up these many values, right? And so the sum of those will be much larger than this sum on the left, right? And this compound B and compound A. So just two conformational isomers. And so consequently, right, if we now go back and look at what that means for our equilibrium constant, hang on. Yeah. So what delta S is logarithm QB over QA, right? And so delta S is much larger, 0, right? And hence the equation should be written as such, right? You will encounter much more B than A in a mixture of the two. You could also, this kind of argument, right, I just made by where so I said QA is the sum over minus beta epsilon J, right? QB sum over E minus beta E J. So partition functions, right? That's one way to think about it. You would arrive at the same conclusion using S using directly the entropy minus KB sum over pi logarithm pi, right? So the minus sign cancels with the minus sign of the logarithm of a probability, right? And so the difference between the two states will result from differences in summing all these probabilities, right? And now the probability, if you have few terms and the probability goes down equally fast, then whatever term has more, whatever sum has more terms will win, right? So this is a manifestation of how to intuitively think about entropy contributions coming from two competing reaction pathways, for instance. You should think about how dense is the spectrum of the corresponding Schrödinger equation to predict which way it's going to go. Are there any questions on this? So this was one case. Now let's consider another case. Again, two conformers, but now we like to have a case with the spectrum where again one spectrum is not that dense, but now the dense spectrum is higher up. And so A and B are in equilibrium. And now your delta E0 is not equal 0, right? And so the question is what will happen under these conditions, right? And it's very clear in the case that your temperature is 0, right? And let me draw an example of this case. Imagine a conformer where I have a hydrogen bond that can form, for example, with pyridine ring. Right? I could have an intramolecular hydrogen bond, and this system can be in equilibrium with the hydrogen link. Now, clearly on the left, due to the hydrogen bond, you gain a lot of enthalpic energy, right? But you lose in the vibrational freedom, right? So there's no rotation you can do around this bond, while here you can happily rotate around it, right? Similarly, on this side, you can rotate around this bond, but not on the left-hand side, right? And so what happens then is that this delta E enters in competition, right, with your entropic term, right? Now, the delta E is temperature independent, and your entropic term will grow with energy. So we know that the equilibrium should be like this for t to 0, right? And like this for t going up, right? Or large t. Let's put large t. Obviously, your t can be too large because then your system will decompose and so on. So there's also a limit to that. This is what how we can distinguish these regimes, right? Now, the first case is something we would call an exothermal change, right? You're freeing this delta E0 is basically a gain, and if you observe the second case, that's an endothermal case, right? So this would be a case where the attraction by the dense spectrum, right? Your entropic attractor must suck out the delta E0 energy from the environment, right? So such endothermal processes are very typical when you evaporate solvent, right? And that's typically a case like this, right? Your solvent molecule enters the gas phase, has much more entropy, much denser spectrum, but it has to pay for that gain in entropy by enthalpy. And so it cools down the environment, right? And this, of course, the cooling effect you're all very familiar with when you go swimming and then the wet water on your skin evaporates. It has this cooling effect. It's also used in cooling devices, right? Evaporative cooling, and this underlies this principle. Now, we can, of course, also include a trivial example where we have energy and system A has a very dense spectrum and system B has a high-lying core spectrum. And this means that there's no way that spontaneously you would ever form B, right? And this is, in other words, an hexagonic process. And if you wanted to observe the endergonic process, you would have to pay not only enthalpy, but also the corresponding energy for the entropic contribution. We've reached the full hour. Are there any questions regarding today's material? Doesn't seem to be the case. I'd like to thank you for your attention, and I'll see you next week. Bye-bye.